Okay. So what I'm planning to do for this session is discuss exercise questions of Module 3 from the textbook, because I think there are some really good questions in that, and questions that you could be asked from this module. And again, whatever I'm working out, I'll share that document also. Okay, let me share my screen. And yeah, now we have 60 members in our team, which is good. We had only 40 or something last time. So if you know somebody who's trying to join the session, you can share the team link. This link is supposed to be for all C1 slot students of computer science, of course, computer networks. So yeah. Hmm. Okay, session 3. And so all the questions that I'm going to take are questions from the textbook. And just some very simple and theoretical based questions. First, we'll move on to more complex things in a few questions. CSMA CD and CSMA CA, I think, is visible.
Yeah, it is.
It is? Okay, okay. Yeah, so it's just screenshotted from the textbook. CSMA CA, CSMA CD. This is basically, you need to remember what CA and CD stands for if you want to answer this question. CD is collision detection. CD detection. CA avoidance. And so what your answer, if you were going to answer this kind of question, would be CSMA CD. What it does is it's detecting a collision. So it'll find if there's a collision that it finds, it'll detect it. And also what you need to remember is that it's going to, let me write it here. Frame is resend, because it'll detect that a collision happened and it'll resend. It'll resend the frame. Avoidance is prevention. Prevention. So in CSMA CA, the protocol is in such a way that it avoids any collision from taking place. And so that's the basic difference between these two. So if you know what CA and CD stand for, you'll be able to answer the question. Okay, that was a simple summary right here. One. Okay. Mm, Piconets and scaternets. Yeah, this is again, just you just have to remember what is these terms. So in Piconet, what we're talking about is basically Bluetooth. So it's a single Bluetooth network. But the reason why some people don't know, I mean, would get confused, is that it's not an often used term, Piconet, but it's something that they could ask you because it's in the textbook, and I think it should be there in the INSA's PPT also. Scatternet is nothing but, what is wrong? Okay. Scatternet is just two or more Piconets. That's it. That's the only difference between these two. So Piconet is anything if you're taking a Bluetooth network and you are so that the whole network, so source, your destination, everything, when you combine it together, that becomes one piconet. So if you have nodes, two nodes, maybe three nodes, whatever, and then they're connected. They're not actually wired, but it's all Bluetooth connections. And here is another piconet. This node. This is one piconet. This is another piconet, and together the whole thing is a scatter net. Yeah, it's a simple concept. Okay. We're given an address 43 colon 7b colon 6c colon de colon 10 colon 00. And the question says, this has been shown as a source address in an Ethernet frame, and the receiver has discarded the frame. Why? So basically, there's something is wrong with this address. That when the receiver saw this Ethernet address, it discarded the frame. So why? So what you should know is that if there is some discarding from just the address, then there's something wrong with the address. So we'll have to look more. We'll have to look more into what is wrong with this address. And one way we can do that, or the way how you would find out something is wrong, is if you would convert this to binary. For so so let's say 4 is in binary, it's going to be 0 1 0 0, right? 0 1 and 2, yeah. And 3 is 0 1, so 0 0 1 1. And so the way this first block of the address would be written in binary would be this all together, right? So it would be 0 1 0 0 0 0 1 1. This is the address of the first byte, you can say. First byte of the address that the receiver gives. Um, so you'll have to remember that when there is some when a byte is received by a receiver in the so when we talk about the Ethernet frames, when you look there is a the thing is the least significant bit here is 1. And in the Ethernet protocol, if you remember, if the least significant bit in a byte in an address is 1, what that means is it's a multicast address. Multi. What is multicast? We saw it yesterday also. You have one node and it's sending it to many nodes. But it's not a broadcast. Difference between this and a broadcast. Broadcast means it would send it to all the nodes. Multi means it's one to many, but not one to all. So there are some nodes that are not being sent. So we have found out that this is a multicast Ethernet address. Yeah, but that still doesn't tell us why the receiver has discarded the frame. The thing is that it's the thing is that the address is given as a source address. So can a multicast address have can a node have a multicast address as a source? No, right? That does not make sense, because if you have a node, the multicast address would be where it is sending to, and not its address. That's the logic behind this question. So what you would have to do if you wanted to answer this, you would have to write how why this is a multicast Ethernet address, and and how it is not logical for a source address to have a multicast address. Hence, receiver is discarded. It discarded because it knows that some corruption has happened in between in the address. So it'll discard the frame, and then this host will have to resend. So it sends discarded, then this host has to resend the frame with the correct address. Yeah. So since this address could not have been a proper source address, it's discarded. It's instead a multicast address. Multicast. Yeah. Okay. Mm, byte stuffing. Yeah, I think it's yeah. Okay. Question is, they've given us a long string of binary. It's one long data, and they've given us a string of binary values, and the question is to byte stuff the data, right? So what is byte stuffing? So byte stuffing was put. The problem was, so we had flags in the data, and we don't know when there was a group of these 5 or more 1s. What would happen is we don't know whether this is a flag or whether it's the data, because a flag is represented by a string of 5 1s, and we don't know when this five whether the data has those 5 1s, or whether whether the user is depicting a flag, right? So what they did was, byte stuffing, it inserts a byte into the string. Like for example, so what would happen here is, so you have 1 2 3 4 5, and then what you do, it would insert a character here to show that this is not a flag, this is actually data. So actually now the question becomes very simple. So all you have to do is take your values. So 1 1 1 1 1, and I think there are 2 4 6 7 1s. So after the fifth one, you'd have to add a zero. That's all. Then you can continue. 1 2 3. Uh, 1 2 2. So 7. So only two more ones, right? And that's it. Now you can continue with the zeros, 2 zeros. Then again, you have now 6 1s. So you write 5 1s, 1 2 3 4 5, put a zero, and then the last one. Uh, then again, you have a zero. Again, you have a 1. So as long as it's less than 5, it doesn't matter. Again, you have another set of 1s. So here you have 2 4 6 8 10 11. Okay. So the first 5 would come 1 2 3 4 5. You will put a zero. Then another 5, 1 2 3 4 5. Then another zero, and then finally the last 11th one. Yeah, so 11 ones, and then we put 2 5 0, and then another 5, and then 1. Yeah, right. And then we're left with these last values. So there are 4 zeros, 1 2 3 4, and 5 would have 1 2 3 4 5 0. That's it. That's yeah. That's all that needs to be done by step. So the ones that we added, here we added one, here we added one, here's another one, and one. right? Any other? No. So total 5 bytes were stuffed into this data. So the question doesn't ask that, but uh, oh yeah, it's bit stuffing, not byte stuffing. Byte would be 8 bits a bit. So each one of these are single bits, not bytes. So 5 bits were stuffed into this data, and so this is the answer for this question. Okay, that was question 4. Mhm. Okay, next question. Yeah. Okay. So okay, sorry. Next question says, this is again from everything's from the text. So it says, assuming even parity, find the parity bit for each of the following data units. And you're given these set of data and you're supposed to add the parity bit. So I'm not sure whether you have done digital logic course yet, but we had parity bit there also. So basic idea is, if let me write. So even parity implies that we need to get even number of ones. So all ones should be even. That's all that we need to do. So if you see the first word, 1, 0, 0, 1, 0, 1, 1, is the first one. How many ones does it have? It has 4 ones. So it's already, so 4 ones means we're already even. And so because of that, the parity bit will be 0. If, for example, we'll see in some other examples, if, for example, there were 3 ones, then we need to add one more one to make it even, right? If we had 1, 0, 0, 0, 0, 0, now all you have is 1, 1, which is not even, and so the parity would be equal to 1. That's all. So we can quickly do this. So second one is 0, 0, 0, 1, 1, 0, 0. This has 2 ones, so it's even. So the parity is equal to 0. 1. Oh, so yeah, this is the example that I did. 1, 0, 0, 0. 0 has only 1, 1. So that's odd. And that's why the parity will become 1. The last one has 6 ones. So that's already even. Therefore, the parity will be 0. Parity. Okay. So so what you could do, so how it is done in the network is, you would append the parity bit. So you'd have parity bit, and then you'd have the data, the normal data. Yeah. So parity bit and the data. And so your final answer for something like this would be, you would just write the parity bit. So for example, the first one would be 0, and then you just write everything after the data as it is. So this is what you would call code word. This together. So let's write code word. So it's just the parity bit appending to the beginning. Code word. Um, okay, yeah. So we can finish the rest. B would be 0, 1, 2, 3, 4, 1, 1, 0, 0. Oh, there's an extra 0. Okay. Third one would be 1, 1, 1, 2, 3, 4, 5, 6. D would be 0, 1, 1, 1, 0, 1, 1. The aim of even parity is all the data that you have should finally be of even parity. Even parity means one should be you. So after the final code word that you get should have even number of ones. And so that's how it is. 4 ones, 2 ones, 2 ones, 6 ones. So these are all even parity. So it was made even parity because we added one parity bit. And that parity bit was dependent on whether it already had even ones or not. So this would be your final answer would be this thing here. Yeah, that was fifth. Yes. Okay. Mm. So then a very easy question. I just want to quickly mention. Apply XOR on the following pair of patterns. You're given two patterns, two data, and you're asked to XOR. You should just know that. So I'll type it. 0 XOR 0 is equal to 0. 1 XOR 1 is equal to 0. And when they're opposite, 0 XOR 1, that's 1. And 1 XOR 0 is equal to 1. So that's all you need to do. So you do it bit by bit. So I like the first one. So 1 0 0 0 1 XOR 1 1 2 3 4. Yeah, 4. So that would be 0 for the first bit, because first bit you're going to be looking at this one and this one, 0, and then you would move on. Second bit will also be 0, third bit will be 0, fourth bit will be 0, and fifth will be 1. That is what you will be doing. And only thing that is different is they're asking what do you infer from this result. So you will see that. Oh, actually, let's solve it then. Then we can make an inference. So the first one, there's nothing to infer. Let's quickly do this question. P is, so you have 1 1 2 3 1 XOR 1 1 2 3 1, and it's going to be all zeros that you'll be able to see. And the inference is basically if you XOR one data with itself, your data becomes null. Your XOR value will be null, will be all zeros. And then C, 1 1 0 0 XOR 1 1 1 is a 0. Yeah. And what you'll get from here is 1 1 1 0 0. Yeah. So the inference here is if you XOR a value with null data, you will get the same value. So this is like identity in XOR. And for the final one, so you have 1 0 0 1 1 XOR 1 1 1 1. So what will it be here? 0, 1, 1, 0, 0. Right? So 1 and 1 is 0, 0 and 0 and 1 is 1. Is 1 is 1 and 1, 1, 0. So what is this? What is the relation between this result and the first result? It's actually the complement, the one's complement. One's comp. So that's the inference that they're looking for. The identity, the how to get a complement, the inverse. Yeah. Um, this was how do you get the null? This you do with itself, and the first one was just normal XOR. Okay, so this was it was a simple question, but only the inference that you needed to you needed to find out. Okay. Mhm. This is a more numerical type of question, and yeah, it's the question says suppose the length of an IOB is 5 cable is 2,500 meter. If the speed of the propagation in a thick coaxial cable is this meter per, it shows what speed meter per. How long does it take for a bit to travel from the beginning to the end of the network? I assume there are 10 microseconds delay in network. It's actually a very simple question. So you just need to use your basic formulas. So time is, so like speed is distance by time. And so time would be distance by speed by speed. And so the question is how long does it take for a bit to travel from beginning to end? It would you just have to do the division between these two. So the time to reach would be 2,500 divided by 200 to 3, 1, 2, 3. Yeah, yeah. And so when you would solve this, I think so. I can see the solution. So it's going to be 12.5 microseconds. But yeah, it's actually a very easy calculation to do. And if you stop here, there's one part that you also need to add. There's a delay in the code. And that delay there, you don't have to do anything with it. All you need to do, yeah. So the total time would be 12.5. Everything is in microseconds plus 10. 22.5 microseconds. That's it. That's all that you need to do. So the final answer of this would be 22.5 microseconds. Yeah, that's this question. It's a simple question. It's just time, speed. Then you need to remember to add this delay. The delay is only going to increase the time, the total time. Right. So that was a. Mm, There is a question. It's asking for, so it's a diagram question. So you have to draw a diagram. And since it's from the textbook figure 11.1, what it is so you have a frame, and so stop and wait, stop and wait protocol. So what happens in stop and wait is, so it sends. So let's say this is the sender and this is the receiver, right? And what happens is the sender will send something to the receiver, right? And then there's a timer. So let's say the timer, also their timeout is 6. So sorry. So after 6 seconds, if it doesn't get an acknowledgement, it will send it again. So let's say the distance between these two is 6. So this is basically how you would draw stop and wait. If there was an acknowledgement would come through here. So this is, let's say this is A, the acknowledgement. This is the sender side, this is the receiver side. And for this question, I'm just going to copy the diagram from the text. So if you give me a minute. Yeah. Oops. Yeah. So what they're saying is, uh, you have a timeout of 6 milliseconds. That means 6 milliseconds before something is sent. So one thing you have to note is, if this acknowledgement doesn't come back, only will this 6 seconds happen. So let's take another example where the acknowledgement does come back. So you have sender, receiver, it goes, acknowledgement immediately comes back, and then next thing is sent. So I hope this is so you'd have data going this way, and acknowledgement came back immediately, and then data would come back. So here, do we need any timer? We don't actually, because timer is if we're waiting for the acknowledgement. Maximum time we can wait for the acknowledgement, this is what the time is. So here there's no time. So what will be the time from one to the next? It will be how long it takes for this data to travel and reach the receiver, and how much that data from there would take to travel and come back as an acknowledgement. That is given in this question. Round trip delay. And so the question only says, so assume no data frame is lost. So when they say is no data frame is lost, what they're trying to say is, no timer, no timer. Not there is a timer, but no timer used. So so the diagram, you can see how it's done. Yeah. So the timer starts and stops because at 4 milliseconds it comes back. It does not go all the way till 6 milliseconds, like in this case. So in this case, let's say there was no acknowledgement that came back. No acknowledgement came back, it will wait for full 6 and then it will send the next. But here, there's nothing being lost. It'll start it, then at 4 milliseconds itself, it stopped. It doesn't go till 6. So at 4, it stopped, and the next frame is it. So this is what you would be expected to draw. Frame coming, going, acknowledgement coming, and 4. Let's say if we change this question. So if we said round trip delay was, I think I can, okay, let's say if we change this question and wrote round trip delay was, timeout was 4 and round trip delay was 6. Now what would happen? So you have sender, receiver. Sender would send to the receiver. So from this node to this node, receiver would try to acknowledge, right? So, but before that happens, the sender would have sent the next one. So timer here is a 4. So for this to totally go all the way here and come back, if it was to come back all the way here, that would take 6 seconds. But before that, the timer will run because it's only 4 seconds. So what you have in this diagram is you not see any acknowledgement. You just see the senders keep on sending his 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 messages because he's not getting anything back from the receiver. So this will be 4. Yeah, so timeout. But on the other hand, if this question, how you see, there is enough time for the frame to go and come back because force is 4 milliseconds and the timer will run until 6. So that's so these kind of diagram questions, you can be asked for. So to draw a diagram, even if it's like they might give you 2 nodes or even 3 nodes. So 3 nodes means from B it has to be forwarded somewhere to C. And how will you draw with mentioning how much time each send will take? Or maybe you could be asked without drawing a diagram. So that is 8. So that is 8A, 8B. I think we are almost out of time. In this module, you have mostly these kind of questions. So you have XOR. Oh, this was theory based. So theory based, you'll have to know full forms of everything. Even there's even another one I can quickly put. mm, like a network allocation vector. So these questions like this network allocation, it's NAV is basically it's for collision avoidance. So these kind of questions you'll have to know the full form. And this was another one where you needed to convert from one address, byte stuffing, parity. All these are not calculation, but just address manipulation. This was in drawing type question. So yeah, I think we are out of time now, and I just want to say uh, everybody who's joined, please fill the attendance. And yeah, that is the end of this session. I yeah, thank everyone for joining, and we'll see you in the next session. Okay, bye.